Here we're looking at a sort of specific example of our Claisen-esque. So it's not really Claisen. And where we ended that last Claisen video was that when we looked at an ester, we had these alpha hydrogens that were potentially acidic, and they could then undergo our Claisen reactions. Well, one of the structures that appeared in that video was this structure, the malonic ester. And so what this section is now referring to is kind of a special case of our esters. In the case of the malonic ester, it's a diester. And in the case of the acetoacetic ester, it's really a dicarbonyl. And so what we're trying to address with this particular section is this juxtaposition of the two carbonyls next to each other. Okay, so if we think back to our alpha beta unsaturated carbonyls, we had particular chemistry associated with it. We had two electrophiles, so we had 1,2 and 1,4 additions. And that was because we brought those functional groups close enough to each other that they could affect each other. A similar thing is happening in these cases, okay? Except the carbonyls aren't directly affecting each other because of the kind of overlap of their orbitals. There is none. Okay? But what is important is that middle carbon. Okay? And if we're going to kind of reference this, which is what the images are trying to show here, if we reference this as kind of our core carbonyl, if we go alpha beta and we see another carbonyl, okay, well, that's going to bring in some interesting chemistry. So let's first address the largest aspect of that chemistry. Regret already having deleted that. And that largest aspect, or first easiest aspect, has to do with the hydrogens at that alpha position, the one dead in the middle between those two carbonyls. Those hydrogens are now very acidic. Okay? pKa, I think in the 9 range. I honestly don't remember that one, but I think it's pretty close. And that's because if we removed that hydrogen through an acid-base reaction, we would end up with a negative carbon, which isn't particularly stable, but that negative carbon can do resonance one direction, placing the negative charge on an oxygen. Note, we're looking kind of at a keto-enol, or we could have done the electrons the other direction. So we end up with two places to displace that negative or electron density, which then vastly improves the stability of the overall molecule. The colored ones that we have there, the red and the purple, are ultimately going to be our more sort of stable structure, so not the useful DUE structure. The useful structure is the one in black, and that one becomes important because that black carbon is now a nucleophile. Okay? Which we did that with our esters. So why is this such a big deal? Well, the first big deal is that the pKa drops significantly. If we look at the pKa's of our esters, they're significantly higher than 9, so we need to use a pretty strong base to get them to do anything. If we move to this diketone or this dicarbonyl functionality, the acidity goes up so much that I can get away with using pretty weak bases and get decent yields. So that's pretty phenomenally useful and cool. Push this even further, we now have a carbon nucleophile. We can do substitution reactions, which, yeah, we can do substitution reactions once we've got that carbon nucleophile. There's our carbon nuke. We can go through, do our reaction, and fantastic, we've now chain elongated. Okay, all of that is pretty special and cool. Okay, but really none of that is the crucial part. Okay, and the crucial part we'll see here in a second. I want to take a step back and look at naming. You'll hear these referenced as the malonic ester and the acetoacetic ester syntheses, and that's the important part that's going to come up, is so kind of genuinely unique and powerful and controllable that these reactions, in particular these reagents, got named for that material. So the malonic ester is that diester, the acetoacetic, here's our aceto, okay, and here's our acetic. So by linking those next to each other, that's where that name is coming from. Yes, that is not proper IUPAC nomenclature. You're also not really responsible for naming it, so don't stress there. I just want you to be able to recognize that pattern. Okay. Before we run into too many problems with let's change the structure and now put a phenyl ring on here. Does that mean we have a whole new reaction? No. Remember, the chemistry is at that alpha position. Okay, and as we'll see, it also carries out to this piece. Okay, I don't care what these groups are out here. Those groups are ultimately irrelevant. Okay, so don't be kind of sidetracked by other functionality showing up. Look for that core middle part. Okay, so now, why? Why do I care? I mean, it's not even just that I'm adding one thing. I'm adding a whole crap ton of stuff. Okay? If we look at the general mechanism provided down below, you'll see Cardi was kind of nice and put in the squiggle so we could apply this to either the ester or the acetoacetic. Okay? If we look at our new structure, we're adding this big, old, gangly, awful looking thing. Why? Why would I want to add so much stuff? Okay, and I'm a little nervous. Okay, cool. That big old stuff is added for this reaction. So the very next step, after we run our SN2, so we do our acid base to get the active nucleophile. Now that we have a nucleophile, we can do an SN2 reaction, do some chain elongation. Then we add an acid and heat, and wait, where the hell did all my pieces go? A whole bunch of stuff has just kind of disappeared from the structure. And that's kind of interesting. Okay. This whole piece is no longer out there. Okay. The important thing to acknowledge in this case is that really what we have added is 2 carbons. And if we were the acetic, we've added 3 carbons. Okay. And what makes that powerful is that now instead of adding big long chains, I can add very specifically short amounts. I can add 1 carbon, I can add 2 carbons, I can add 3 carbons. And for those people saying, well, why do you need that specificity? Kind of a bad reference. Ask the DEA, ask Walter White. The whole point of meth is literally adding a single carbon to your structure. You add 1 carbon, boom, you can become a drug kingpin if you can figure out how to do that easily. So the specificity of being able to add very few carbons correctly is kind of important. Okay? And so that's why this synthesis is so useful, is that we can run with a relatively large piece and end with just adding 2 carbons or just adding 3 carbons. And so we could progressively grow a structure kind of very methodically and carefully, and that's useful. So, kind of neither here nor there, how the F did this happen? Right, so we did address one of the big things. The big change was all of this has somehow disappeared. That is an awesome face. Okay, well, how? How did it disappear? One of the misleading steps that you might undergo as a student is say, well, what am I doing to get rid of this? And I would argue that that is actually the wrong approach. Okay? What you should be looking at is what is the most reactive thing present? H3O+. Okay? So that's reactive because it gives me H+. This is now going to set me up on the right path because what do I need to do in my first step? Well, neutralize the H+. To do that, I need electrons. Those electrons I can pull from the pi bond, okay, or from the oxygen, depending on your mechanistic decisions. Okay, And this is going to be a bit weird and a bit long, so kind of bear with me as we walk through this. And you might say that the protonation, and fairly, that protonation is not a huge issue. It didn't really do a whole lot, right? Except that what it did do was it set up that oxygen to not want to be positive, and it is now polarized that bond. And that becomes important because I've now found a very reactive carbon, okay, in that carbocation. So I need to neutralize that. Okay, just like I found the hydrogen, now I found a carbon that's positive. I would need electrons to do so. The electrons in the ester structure aren't particularly useful, and this is where, if we always keep in mind what's going on with our reagents, that H plus came from H3O plus, meaning I also have water floating around. Water can come in and attack. The result of this, not particularly exciting, okay? And it should look kind of familiar to you, because what we're moving through would be known as kind of a transesterification. That's not the right word, but we'd be moving down our activity ladder from an ester to a carboxylic acid. Our solvent, H2O, could come in, deprotonate. We would have our awfully substituted carbon, okay? And as we talked about before, that is not very happy with all of those electronegative elements connected to it. So it would undergo another protonation. And you might say, well, which oxygen do we protonate? Right? That is a valid question, and the conclusion of that valid question gives us these green arrows, which I'm now going to show, that each and every single one of these steps is an equilibrium step, okay? Which means we don't expect a whole lot to happen. And again, you might be like, well, what the F? Why are we chasing down this path if nothing useful comes out of it? Well, that's part of, exploring. Let's see where we go. Okay, and this is one of the things that makes second semester so challenging, is you may have to go quite a distance before you actually find something useful. Whoops. So now we have a great leaving group that can leave. The electrons can come back down. Should have left that as a red arrow. And we did all of that in the presence of that acid. Again, equilibrium. And I keep leaving off that R group. That R group isn't going anywhere. And we would now have our carboxylic acid. Okay? And you would rightly be like, well, that's kind of dumb. Why did we go through and do that? Okay, well, we aren't there yet. Okay? The other thing I want to address or show here is because we've already gone through a whole bunch of steps, and this protonation, deprotonation stuff sucks, we're going to do that deprotonation very quickly, and we're just going to end with our first product, the carboxylic acid. So all we've done with the addition of this acid and water as a nucleophile was convert the ester to a carboxylic acid. Woohoo. Why? Why does that matter? Okay. The next part of this that might kind of trigger some alarms is that we're also seeing the symbol of heat. Okay. And heat tends to suggest eliminations. And so far what we've done, while we have done some nucleophilic or nucleophile eliminations, that's what happened back over here. This was a nuke elimination. Whoops, that one was acid base. This one was our nucleophilic elimination. This one was acid base, because we're here, acid base, nucleophile addition, and acid base. So like I said, lots of acid base. We never talked about heat being important when we converted our acid derivatives, esters, into acids. That was a relatively straightforward thing to do, and it just depended on acid catalysis or pulling Le Chatelier principle stuff. Okay, so why then do we have that heat? Okay, so I'm going to delete everything just so we can kind of restart this. We went through that whole process, and what we ended with was the carboxylic acid. Okay, we know this piece has to somehow disappear. Okay, a hint to help us with this is that one of the byproducts of the reaction is also plus the formation of carbon dioxide. And if I go through and look at that piece after I've converted the ester into an acid, what do I have? I have a carbon, and I have two oxygen. That looks like carbon dioxide, but it is still connected to the structure. So I need to do an elimination, which means a pi bond needs to form, and I need to lose a leaving group. Well, could this be a leaving group? Okay, could this be the leaving group I'm looking for? Well, let's consider it. CO2 has two double bonds. I only have one right now. That oxygen-hydrogen bond, that's an interesting bond. How about let's take the electrons from that hydrogen and let's put them in to make a pi bond. That would mean I'd have H plus floating around. H plus was catalyzed in this reaction, so meh, not a big deal. I also conveniently drew it in such a way where that oxygen could intramolecularly pick it up. So let's clean up some of that so we can see that. And for those of you saying, but intramolecular reactions are not likely to happen. True, because they're usually happening with a three-membered transition. And if we go through and look at this, 1, 2, 3, 4, 5, 6. That's a six-membered transition state for that protonation, deprotonation. So that's fair game. And in fact, that's actually fairly likely to happen because the structure is going to naturally align to that. Okay? If we go back to our pi bond, okay, the formation of that pi bond, which I've now colored as blue, that would mean that carbon would exceed its octet. I can't do that. So we would have to break a bond. One option would be to break the other pi bond, but again, what's our focus? The focus is that roughly circled thing needs to leave the structure. The carbon has too many electrons, so let's take the electrons in the sigma bond, and let's shuttle them this direction. Okay, a lot just happened here. Okay, a lot. Take a look at that new carbon. That's now exceeded its octet. Shuttle electrons. Okay, I am going to clean this all up and we'll look at it again in a second. What is the end result? Squiggle, nothing happened. R group, nothing happened. That bond has disappeared. I have CO. I have CO2. That bond has disappeared. I have a new bond to that oxygen. That pi bond disappeared, and I have this new pi bond. The end result, I lost the structure, and I formed a pi bond. That is an elimination reaction. Yeah, the heat was used to do an elimination. And that's why that CO2 left the structure, known as a decarboxylation. Okay? We have to have very particular alignments to allow for the decarboxylation to occur. Our leaving group, CO2, has to be stable. Great. But just because we have a stable leaving group does not mean the leaving group leaves. Read this situation back in substitution. that carbocation is unstable, okay? So we have to be careful to evaluate what's going on within this to ensure what has occurred. So let's backtrack. I'm going to erase all of that right there. Let's try and draw that again. Whoops, that's supposed to be a squiggle. The electrons, the electrons, the electrons, the electrons. Okay. I'm going to take a small break here, and this pi bond, or those electrons, I'm actually not going to fold all the way across. I'm going to go to there. So I'm just going to go to that atom, which is going to change the result of my product here. So let's go through and clean this up. The pi bond is still there, right? I didn't break that pi bond. Hydrogen I've gotten rid of. This I've gotten rid of. Right? The oxygen, having 3 bonds and a lone pair, becomes positive. And now we would ask ourselves, was that allowed? Okay. Remember how we said the CO2 was the leaving group? Well, the leaving group leaves with the electrons. Did CO2 leave with electrons? Well, no. If anything, what left, it left as a positive. What left with the electrons was this structure. This is my leaving group. CO2 is effectively the substrate, if you will, and fell off the structure. The leaving group is what we're carrying forwards. That leaving group must be stable, because if it's not stable, we can't form it. Why is it stable? Well, if we, oh, come on, connect. If we drew out the resonance, this would be a good opportunity for you to draw out that resonance structure while my computer frantically reconnects. And if we drew out that resonance, what we would see forming would be what functional group? An enol. The whole reason this reaction works is because of the stability of the enol. Okay? That enol must form in the course of this reaction, which means when we backtrack outwards, there's our negative. That negative needs to be forming on a carbon that is alpha to the carbonyl. When does this occur? Well, this occurs when we have an alpha beta diketone. We have to have that alignment, or dicarbonyl. One of those has to be an ester, so that that can be converted into the acid, so that that could be converted into CO2. Okay? Beginning to end, what we are looking at is what is known as a decarboxylation. The decarboxylation is this really important result because the end result is that we're adding very limited amounts of carbons to our structure. Either 2, or in the case of the acetoacetic ester, 3 carbons. Okay? It is that power that is fantastic. This is the chemistry associated with this is really fascinating and cool because we're going back to those same basic tenets with our enols and nucleophiles and all of that stability. Okay, so it is an awesome reaction in that sense. It is also an exceptionally challenging reaction to memorize because you will be given the question, which of the following things could decarboxylate? And you will now see a sequence of species that all have, potentially all have, 2 carbonyls. Good, that's important. So just the straight up acid can't decarboxylate, okay? Why can it not decarboxylate? If this left as CO2, we'd be putting a negative charge on that carbon. That is not stable. We can't form a negative carbon easily, which means that does not decarboxylate. The rest of them have carbonyls. You go, oh, well, because it has 2 carbonyls, it must be allowed to decarboxylate. No. Again, it's that ability to form the enol. What we're doing is removing that acid and putting a negative charge. Remove that acid, put a negative charge. Remove that acid, put a negative charge. Only when we have the proper alignment of the dicarbonyls that we're actually going to get this. The name associated with this is a beta keto ester, okay, because the ester is our highest priority functional group. If we go alpha beta, we have to have that beta keto functionality, okay, and really it's just beta carbonyl ester, okay. Super neat reaction, super challenging one for students to go through and look at because you try to over memorize it. Follow the chemistry, let the chemistry run it for you, and you can get to that answer a little bit smoother than if you just try and memorize it, because it's easy to lose connection of those pieces. Okay. If we look specifically at the acetoacetic ester synthesis, we're starting with acetoacetic ester, and that's what drives it. The first step is typically a base to make a nucleophile so that you can do a reaction with an electrophile. So we're doing the acid base to activate the nucleophile, followed by the SN2, chain growth, followed by conversion to the acid, ester to acid, followed by decarboxylation. Sometimes you can do the conversion to ester to acid under base conditions or under acidic conditions. So it largely depends on the system you're trying to do. Why would you vary that? Okay, well, in this case, we do have that alkene, and alkenes are sensitive to acid. We might want to limit the exposure of this molecule to acid because it might end up doing some goofy chemistry down there with the alkene. So that might be a good reason why we try to convert the ester into the acid before we did the decarboxylation. Okay. And then referencing back to these, this was our SN2. This was our activate nucleophile. Okay. End result, if we go through and look at it, we get 1, 2, 3 carbons. The acetoacetic ester was a +3 carbon synthesis. Again, controlled chain elongation is a very important thing. Okay? If we switched to the malonic acid, and not only controlled chain elongation, but we also maintain some reactivity in that chain elongation. We've now got a carbonyl that we could potentially convert off into a myriad of other pathways. So it's not just chain growth, but it's also keeping some functionality so that we don't have to chain growth and then do a whole bunch of extra stuff to get it back to an active state. It's chain growth and maintaining activity. In the malonic ester, similar idea. Okay? If we break this one down, we've got our acid base activation, followed by our SN2, followed by our acid conversion. So this would be a nucleophilic addition elimination reaction, followed by our decarboxylation. That says decarboxylation. If we look at the end result here, what we've added to our structure, okay, where this piece being our quote-unquote structure, is that we have added 2 carbons and maintained activity through the carboxylic acid. Okay, so it's the presence of those pieces that makes this reaction pretty cool. We can either add 2 carbons or 3 carbons. Fantastic. Right? And maintain chemistry. So recognizing that mechanism is an important one. seeing those pieces, seeing the association of where those groups are so that you can do these decarboxylations. The other thing to kind of just be aware of, because I think that's our last slide for this, why would decarboxylations be relevant? That was a hint. When you exhale CO2. How is the body doing the decarboxylation? Yeah, through a similar mechanism. Okay, it's that bond cleavage, the formation of the CO2 that way, that's ultimately where this is coming back to. So you could fully expect to see, at very least, similar type reactions and mechanisms when you move into biochemistry. With that, I think this is a cool reaction. Hopefully you thought it was cool too. And believe it or not, even with 2 videos left, we're pretty much done because those 2 videos are going to suck.